So in chapter 5.1, we're going to talk about scale representations. So here we're going to do scale drawings and models. Now remember, when you scale something, you essentially take one shape, let's call that a perfect square, and in order to make this thing larger, we have to multiply everything by the same number. So this could turn into 6 and this could turn into 8. So I multiply both numbers by the same thing. That's what a scale drawing is. If I don't multiply by the same number, your image becomes distorted. So it's like zooming in, like right here. I can zoom in, so in order to keep everything proportional, you need to multiply this top part of the screen by the same number by the side number of the screen to make things not look super stretched out, okay? So in order to do this, we just need to kind of review cross multiplication and division. So remember how that works. So you have some examples worked up there. I'll do a few with you here. So in order to solve this, we're going to cross multiply the two numbers and then divide the odd number out. So x is going to equal 30 times 7 divided by 105. And you're going to plug that into your calculator. 30 times 7 divided by 105, and you should get 2. Perfect. And remember, cross multiplication works wherever your x value is, as long as you have something that's set up in this particular manner. So let's try this one here. So here, I'm going to cross multiply these two numbers, so the numbers are crossed, and then divide the odd number out. So 198 times 5 divided by 90. So 198 times 5 divided by 90. And that gives me 11. Okay, so there is a quick little refresher on cross multiplication and division. Now, let's kind of look here. It's sort of the same thing, right? So solve the following proportions. So this side is proportional to this side. So I'm going to do 6 times 12 dividing 5. So 6 times 12 dividing 5. And if I plug that in my calculator, I will get 14.4. So I'll leave this one for you to try it on your own. The answer's there. Make sure you're able to get it. If you're not, you're kind of confused, please come ask some questions. Okay, so let's look at number 4. And remember, these proportions are always true. So if Georgina travels 355 kilometers in 7 hours, how far will she travel in 8.5 hours at the same rate? So let's make a ratio here. So I'm going to put distance on the top and time on the bottom. She has stated that it takes her 7 hours to walk 355 kilometers. She's going to use the same rate here. So I'm going to put my time on the bottom and solve for the X amount of hours. So this is X amount of kilometers in 8.5 hours. Now, where have we seen this? Well, we've seen cross multiplication and divide. So X is going to equal 8.5 times 355 dividing 7. Okay, and we can plug that into our calculator here. Oh. So let's get Notability opened up here. There we go. So 8.5 times 355 dividing 7. And that's going to give us 431 kilometers. So since she used that exact same rate, we can use that. Just like how we do it in trigonometry. We have a slope. That slope is always the same slope no matter how far you go, so you can keep using it. Okay, so from here, we're going to learn a little bit about scale statement and scale factors. So scale factors is something you actually learn in grade 9, and this is where you multiply everything by the same number. So you can figure out the scale factors by dividing certain numbers. A scale statement is just saying that this is like a 3:5 ratio. So that means 3 units on the model represents 5 units on the original model. So you always want, when you state these fractions, a scale factor equals an original number. So you can either do the original number dividing the scaled diagram, or vice versa, as long as you always use the same number on the top and the same numbers on the bottom. That'll make more sense once we do an example. So let's see here. So there's a few worked out solutions for you. Let's go to 7. So Trevor Linden formed a former player for Vancouver Canucks, is 1.93 meters tall. On a hockey card, he is 5.4 centimeters tall. What scale was used to print the hockey card? So recognize, in order to figure out the scale, you need the same units. So what can I do here? How about we convert 193 meters into centimeters? So 193 meters, I'm going to multiply that by 100 centimeters because there's 100 centimeters in 1 meter. Okay, and that's going to give me 193 centimeters. And then from there, we can have our ratio. So let's put real life on this side and card on this side. So here I'll have 193 for 4.4 centimeters. And let's see what that turns into. So 193 dividing 5.4. And there we get, for every 35 units of a real card or of real life, you get 1 unit of a card, okay? And they just used a decimal, pure 35.7. So now, the reason you want to set it up where you have the same units, we can use this for any units, okay? Because the units cancel out. We have centimeters here and centimeters here. So if we had something in real life that had 10, let's say, kilometers, you could figure out how many kilometers are for the card, which doesn't really make sense because that would be a humongous card, okay? But your units have to be the same. Okay, so that's the scale. Let's try number 9 out here. So a beluga whale that is actually 4.2 meters long is represented in a children's picture book with the following picture. So we got a nice little picture here. Measure the diagram and write a scale statement for the picture. So unfortunately, I don't really have a measuring tool nearby, but that being said, I would roughly estimate this to be 1, 2, 3, I would say roughly 3.5 centimeters long, okay? In real life, you'd probably calculate, you use a ruler pretty easily there. But now we have something. So I'm gonna do real life on this side and picture on this side. And remember, I need them to have the same units. So I'm gonna convert 4.2 meters to centimeters. So 4.2 meters times 100 centimeters, and there's a 1 meter in every 100 centimeters, and that gives me 420 centimeters. Okay, so now I can plug these in, and again, the useful part about this is now we don't have to worry about our units because they kind of cancel out. So here will be 420 to 3.5, and let's see how accurate I was here. So I'm going to take 420 and divide it by 3.5, and that'll give me 120. So it looks like I was a little off in my calculations. Let's do 420 divided by 4. Okay, so roughly 120 to 1 units. Obviously, I didn't use a ruler, so my estimating skills didn't work very well. That must be a little bit larger than 3.5 centimeters. Now, looking at it, I definitely agree with them. 1, 2, 3, 4, 5. Wow, that's roughly 6 centimeters. Okay, so you'd actually put a 6 here. My bad, everyone. So let's do 420 dividing 6. There we go, that's much closer. So about a 60 to 1 ratio. Okay, or sorry, 70 to 1 ratio. Okay, so there's our solution for that guy. Let's move on here. So an alligator is drawn at the same scale in the drawing. It is 5.9 centimeters long. How long is the actual alligator? So here, remember, we can represent this as a fraction. Now that we've used this scale can be used a bunch of times. So I'm going to put real numbers on top and pictures on the bottom. So here, my real number is related to 70, and that will be over 1. Okay, so now here, I have a drawing. So my picture is 5.9 centimeters. And I'm trying to figure out what that is in real life. So my x value goes on top. So now I can just cross multiply, divide. So x will equal 70 times 5.9 dividing 1. So what will that give me? That's going to end up giving me divide 1, 413. Okay, and of course that will be centimeters. My answer here is a little different compared to this, mainly because, again, I used a different ratio here because my estimate was a little off, which is okay. So here we can see that if my picture is 5.9 centimeters and I use this scale, then I get 413. So remember, if you want to put the real numbers on top, you always have to keep that consistent. Okay, we could have flipped this and put 1 over 70, but then we'd have to put 5.9 on the top. Now, remember, what was the point of getting 4.2 into centimeters? Because now this scale can be used regardless of the units you're doing. So here again, this time I'll put pictures on the top and real on the bottom. So it'll be a 1 to 70 ratio. For every 1 unit in my picture, I get 70 units in my real. Here, I don't have to worry that this is in meters because when I set up this factor, this scale factor, well, this is unitless because we made them into the same unit, so it cancels them out. So we can use this anytime, regardless of the units. So we're trying to figure out how tall an ostrich be in a picture. So my top number, x, is what we're looking for. So the picture, when the real image is 1.9 meters. Okay, and let's solve for that. So x will equal 1.9 times 1 dividing 70. So let's see what that becomes. So 1.9 times 1 dividing 70. And that gives me 0.0271, and that's going to be in meters because this thing is in meters. Okay, if we times that by 100, we can get it into centimeters. So this is 2.71 centimeters. Okay, that's how big our picture should be. Again, we're a little off, actually not that much this time, but we're just a tiny bit off because we used a different factor than what they would have used up here. Okay, so again, you make your original factor using the same units, so then you can use any units when you use the scale. Okay, let's try and move forward here. So a 7.8 meter object is represented in a picture as being 1.5 centimeters. What is the scale factor? Okay, so remember, scale factor is simply just figuring out that scale ratio. So here, I will do picture over real. Okay, and remember, we need to have these as the same units when you first try and find that scale factor. So I'll convert this into centimeters. 7.8 times 100, and that gives me 780 centimeters. So my real object is 780, so this will be 780, and then my picture is 1.5. So let's see what that gives me for my scale factor. So 1.5 divided by 780. Okay, that gives me a pretty ugly number. Now your calculator has a pretty neat tool where you can press math and then you can press fraction. Okay, and that will give you 1 over 50. Another way to do that, if your calculator is unable to do that, is you're technically just dividing the top and the bottom by 150. So here I could do divide by 150, and that will give me 1. Divide by 1.5, and 780 divided by 1.5 gives me 150. Your scale factors, you usually want one of the numbers to at least be 1. Okay. So let's go on to number 2. The shoreline of Great Bear Lake is approximately 2,719 kilometers, not counting islands. If a map is drawn with a scale of 3 centimeters per 100 kilometers, how long will the shoreline be on the map? Okay, so it's really important to understand this is not unitless. Okay, so it looks like we put drawings on the top and real life distances on the bottom. So this is drawing over real, which would be 3 centimeters over 100 kilometers. Since we did not use the same units, you have to keep units consistent, okay? So let's see here. It wants us to, how long will the shoreline be on the map? So the shoreline, I'm assuming, is this guy here, okay? So we have a nice little ratio here. So from here to here is roughly 100 centimeters, or sorry, 100 kilometers. So that would roughly be this guy and this guy, if that's what it's talking about on the shoreline. So I think the shoreline, they actually want us to go all the way around there. So and I would say that's roughly 100 kilometers itself. And then that's roughly 100 kilometers. That's roughly 100 kilometers. That's roughly 100 kilometers. That's roughly 100 kilometers. See how accurate I get on this. That's roughly 100 kilometers. There's another 100 kilometers. There's roughly another 100 kilometers, and then a bit. So how many did we count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's see how accurate I am here. So this would be 11 times 100 kilometers over X amount of centimeters. So here, oh my goodness, I read the question wrong. I made that way more difficult. So this is important. I'm going to keep this in because you should always read the question a few times. So it tells us the Great Lake is approximately 2,719. So this is just a visual. So here, we simply have to plug this in on the bottom because it is the real life distance and you're solving for X. So how large it should be on your map. So X equals 3 times 2,719 divided by 100. So here I'll get 3 times 2,719 divided by 100. And that gives me 81.57. And remember, this is the drawing, so this will be measured in centimeters. Okay? Sorry about the confusion there. I was making that way more difficult than I had to. Okay, and they rounded it up to 1 decimal. Okay. And let's do number 4 and 6, and then we're good to go. So number 4 here, the tallest building in Canada is First Canadian Place in Toronto. The tower is 298 meters tall, and the antenna reaches to 355 meters. A model of the building without the antenna is 11.9 centimeters tall. What scale was used to model? Okay, so I'm going to do picture over real. Okay, it's always good to state this, especially for me when I'm marking your stuff, because I want to know what number represents the top and what number represents the bottom. Okay, the tower is 298 meters tall, and the antenna reaches to 355 meters. A model of the building without the antenna is 11.9 centimeters. So we want to compare without antenna to without antenna. So that's 298 and 11.9 centimeters tall. Okay, so here my picture is 11.9 centimeters. Now what's the problem here? The problem is this is in meters, this is in centimeters. So let's convert 298 centimeters to meters. So what do? Well, I simply, this is in meters here. I multiply by 100, okay? So 100 centimeters, so that's gonna give me 298,000 centimeters. So if your calculator doesn't have the fraction button, how do I make this top number a 1 and this bottom number a new number? Well, I'm going to divide both by the top number, because 11.9 divided by 11.9, that gives me 1. 298,000 divided by 11.9, that gives me 2,000. Oh, did I add a 2? I added a extra 0 there, so it should actually just be, there we go. Thought that number looked kind of weird. So 29,800 divided by 11.9. Oh my goodness. And that gives me 2,504. Okay, so there is your solved solution there. Now it says, how long will the antenna on the model be? Okay, so far we have this scale factor where we have picture over real, and here we have 1 over 2,504. It wants us to know how long the antenna will be. Well, here we have a few things going on. Let's make a really bad looking drawing. And our question tells us that the antenna reaches to 355 meters. So all the way up here is 355. The building itself is only 298 meters. Okay, and that's found here. So now it wants to know, how long should I make this on my drawing? Well, first I have to find that. So I'm going to find x here. And x is simply going to be 355 minus 298. Okay, and remember, that is the height of the antenna there. So here I'll get 355 minus 298. And, oh, I accidentally plugged in the wrong number there, minus 298. And that equals 57. So this is the antenna in real life. And remember, that's meters, okay? So what I'm gonna do is I'm gonna do 1 over 2,504. And remember, the real goes on the bottom, and we're trying to figure out how much this should be in picture. I'm gonna make this into centimeters, so my answer comes out in centimeters. So 57 meters, if I times that by 100, that equals 5,700 centimeters. So I'm going to put 5,700 on the bottom here in centimeters. And now let's solve for y, okay? And this is the image length. So I will get 5,700 centimeters times 1, dividing 2,504. So let's see what that gives me. So that will give me 2.28 centimeters. So that's how big I should make it in my drawing. And you can see we were able to get that answer. Awesome. Now maybe I'll give number 6. You guys can try this one out on your own. Okay, so see if you can get 16 on your own. And I'll leave that one for you to give it a shot. There are some useful links down here if you want to look through some videos to learn about scale factorings. Okay, so I hope that was helpful. Sorry for there are a few mistakes. Especially on number 2, that was a bit of a blip in the matrix, but that's okay. We were able to figure it out from there. Other than that, guys, if you have any questions, please contact me. If you need to pause the video, rewatch some of it, go ahead. Have a good day.